Have you ever stopped to think about what's actually happening inside your computer? I mean, how is it possible that you can be typing an email while you're streaming music and downloading a huge file all at the same time without the whole thing just grinding to a halt? Well, today we're going to pull back the curtain and look at the hidden genius that lets our computers multitask so seamlessly. Let's dive in.
It sounds like a pretty simple question, right? But the answer, well, the answer is surprisingly deep. You see, every single time you press a key on your keyboard, you are kicking off this whole chain of incredibly sophisticated operations. Answering this one little question is actually the key to understanding how our computers manage to do so much at once.
So the whole issue, the entire problem, it really starts with a fundamental conflict. At the very heart of your computer, you've got the processor, the CPU, and it is just mind-bogglingly fast. But it has to communicate with a world of other devices that are, by comparison, incredibly, painfully slow. Okay, so here are the main players in our little drama. You've got the central processing unit, the CPU. That's the brain of the whole operation. It's connected to the main memory, which is where it does all its thinking. And then you have the input-output system, or I/O. That's its connection to everything else: your keyboard, your mouse, your hard drive. The problem is, the CPU basically lives in a completely different time zone from that I/O system.
And when I say different time zone, I mean the speed gap is just staggering. A CPU thinks in nanoseconds. That's billionths of a second. But a human typing a character, or even a fast hard drive finding a file, that stuff happens in milliseconds, thousandths of a second. That is a 1,000,000-to-1 difference. Forcing a CPU to wait for you to press a key is like making a supersonic jet hover in midair to wait for a snail to cross the runway. It's just a colossal waste of power.
So how did the early computer designers even begin to solve this? Well, the very first method was the most straightforward one you could think of, but it was also the most inefficient. You could call it the "are you ready yet? Are we there yet?" approach.
So the technical term for this is programmed I/O. All it means is that the CPU just keeps asking the device, say the keyboard, over and over again, "Have you got a character for me yet? How about now? Now? Anything yet?" This constant checking is called polling. It's basically the digital equivalent of you sitting there just refreshing your email inbox again and again and again, hoping a new message has finally shown up.
Now, you don't need to be able to read this computer code to see what's going on. See those lines that say wait K? That is literally the CPU, stuck in a waiting loop. It's checking a status, seeing it's not ready, and then jumping right back to check it again and again and again. It is completely 100% occupied, just waiting.
And that brings us to the really big problem here. While that CPU is busy polling, it is totally dedicated to that one task. It can't process your music, it can't update what's on your screen, it can't do anything else useful at all. Your entire multi-billion operation per second processor is being held hostage by a single, slow device. There just had to be a better way.
And of course there was. This led to a much, much smarter solution. Instead of the CPU constantly bothering the device, what if the device could get the CPU's attention, but only when it actually needed it? This was kind of the "don't call me, I'll call you" breakthrough.
This special signal is called an interrupt. So instead of you constantly refreshing your email, an interrupt is like getting a notification on your phone the instant a new email arrives. The CPU can be off doing millions of other things, totally productive, and then when the keyboard finally has a character ready, it sends a little signal, the interrupt, that basically says, "Hey, over here, I've got something for you." It's really cool how it works. The CPU is just cruising along, executing some program, let's call it program 1, then bam, an interrupt happens. So the CPU carefully saves its place, it takes a quick detour to run a special bit of code to handle that device, that's program 2, and as soon as it's done, it just picks up right where it left off in program 1. Honestly, this is the magic that allows for real multitasking. And, this isn't just some clever software trick, it's built right into the physical hardware. You can think of it like a shared doorbell wire. You have a bunch of different devices all connected to it, and any single one of them can ring that bell to get the CPU's attention whenever it needs service.
Okay, so interrupts are fantastic for small, quick events, like a mouse click or a single keystroke. But what happens when you need to move a huge amount of data, like loading a video file from your hard drive into memory? Interrupting the CPU for every single tiny piece of that file would be just as bad as polling. No, for the big jobs, we need a way to offload all that busy work. And that is exactly where Direct Memory Access, or DMA, comes into play. The best way to think about this is to imagine the CPU as a very, very busy CEO.
This CEO is far too important to be interrupted to sign for every single package that arrives in the company mailroom, right? So for these big data transfers, the CPU, that's our CPU, it delegates. It tells a specialist, the DMA controller, hey, I need you to move this entire file from the hard drive and put it into this exact section of memory. Don't bother me with the details, just let me know when the whole job is done. And just like that, the CPU is completely free to go do other important work. It only gets a single interrupt at the very end when that massive transfer is finally complete.
Okay, so we've looked at 3 totally different ways that computers manage the chaos between the super fast CPU and the slow outside world. So how do they all come together in the computer you're probably using to watch this right now? Well, it's not one or the other. It's really a smart combination of all 3. We have programmed I/O, our constantly refreshing email method, which is actually still used for some really simple, low-speed devices. Then you have interrupts, the email notification, which is absolutely perfect for things like your keyboard clicks and mouse moves. And finally, you have DMA, or delegating to a moving company, which handles all the heavy lifting, like large file transfers from your hard drive or over the network.
And this right here is the real takeaway. A modern computer isn't just choosing one of these methods. It's like a master conductor, using all 3 techniques at the same time. It's orchestrating this incredibly complex symphony of polling, interrupts, and DMA transfers that all happens invisibly thousands of times every second, just to create that smooth, responsive experience we all take for granted.
So the next time you type, click, and download something all at once, you'll know about the incredible juggling act that's happening under the hood. For decades, these really elegant solutions have managed to scale with our needs. But as our data gets bigger and our processors get even faster, it leaves us with one last big question. What comes next?